All right, in this video, we're going to learn another tool for finding the volume of a solid revolution. It's called the washer method, and it's going to pair nicely with the disk method. So going forward, we're going to need to make sure we're paying attention to problems like this, where they're going to require us to find the volume of a certain solid, and we're going to need to make a decision as to which method we're going to use. All right, we'll talk about what to look for that as we get into it. Okay, we got our coffee, we got our crayons, we're ready to go. All right, there's also a great GeoGebra demo that we've posted in Canvas that I'd encourage you to go check out and play around with, as it visualizes this volume in a similar way to the one that we used for disk method did. All right, so at the top of your notes, it says, in the last section, we learned how to find the volume of a solid that is generated by revolving a region around a line that is completely connected to the region using the disk method. But what happens if the region is not entirely connected to the axis of revolution? And here is a 2D example to get us started. All right, example 1 says find the area of the shaded region and explain how you did it. Start with blue-green. Okay, so shaded region of this circle has a kind of a 2D washer shape to it. It's a circle with a hole cut out of it, all right? It's a donut, it's a bagel, whatever you want to call it. To find this area of this shaded region here, that's my shaded region picture, we're going to take the area of the whole circle, all right, which is going to be pi r squared, but that radius is already labeled with a capital R. So we're going to say capital R squared. But then we're going to take away, we're going to cut out this inner circle here, all right? The area of that inner circle is pi times little r squared. Notice how the radius of the smaller circle, the blanked out circle, the cutout on the inside is little r. All right, so whatever that is, that's going to be the area of our shader region, all right? The whole thing minus the cutout in the center is going to leave this ring here. You could do a little bit of algebra. You could factor out common factor and factor that pi out of there. And you could be left with pi times, in parentheses, the difference between capital R squared and little r squared. Okay, we're going to take that and we're going to build on it so that we can find volume of more solids of revolution. So this method can be extended to cover solids of revolution with holes by replacing the representative disk with a representative washer. All right, so we use disk method, and in disk method, we stacked a whole bunch of really narrow, really thin cylinders on each other so that we could approximate the volume of a solid that was formed by revolving a function around an axis of revolution. And then we integrated that so that we got the exact volume and not an approximation. So what we're going to do with this is we're going to run into shaded area regions that are not connected to our axis of revolution. All right, so I like to highlight my axis of revolution. So this is our axis of revolution, and I wanted to revolve this rectangle around that axis of revolution. Okay, picture that in 3 dimensions, going up above the paper, down into the table, and back to where it started. That's going to create a different 3-dimensional shape. It's going to create a kind of a donut, a more 3-dimensional donut, a ring, a cylinder with that middle cylinder stamped out of it. Okay, if you've ever, I don't know, lifted weights and you put plates on a dumbbell, similar to that without all of the numbers and info etched into it. So this is going to require a different method, because the disk method requires that shaded area is touching the axis of revolution for the whole kind of width or interval of our region that we'd be integrating. The washer method allows us to do it when it's not. Okay, so what we're going to do is we're going to create these, again, these 3-dimensional shapes that are like a coin with the middle part cut out. These are literal washers that are used to kind of go around the head of a screw or a bolt when you're attaching two things together. All right, so that's where the name comes from, washer method. All right, we got a great picture here. Notice we have this, we carry over this same capital R and lowercase r like we did from the 2D circle above. We're going to use that to represent the distance from the outside of our shaded region to the axis of revolution for capital R, and the distance from the inside of our shaded region to the axis of revolution for little r. Okay, and that translates over to our three-dimensional figure here with the capital R and the lowercase r. Again, they're going to have different shapes depending on what functions we're asked to find the volume of the solid revolution for. All right, underneath it says, if little r, big R are the inner and outer radii of the washer and W is the width of the washer, the volume is given by this formula. Okay, so think about it as just an extension of that cylinder formula, kind of combined with this 2D circle example here, where we're cutting out the inside circle, now a cylinder. And so we've got the difference of those two, or if we factor out the pi, this part here, times the width. So we're gonna essentially use this as our starting point each time we write our formulas for these washer method problems. Okay, I'm gonna call this the volume of each of our slices. All right, see how this concept can be used? To find the volume of a solid or revolution, consider a region bounded by an outer radius and an inner radius, as shown in the image below. If the region is revolved about its axis of revolution, the volume of the resulting solid is given by our integral. Here's where calculus comes in. We're going to take all those washers and we are going to integrate across that region so that those washers become infinitely narrow, to have a width of the limit as x approaches 0. That's our dx width there. And the outer squared minus the inner squared is going to give us that remaining solid cylinder. Okay, we're going to integrate from A to B, left to right, if we're taking dx strips. Just like in the washer, or just like in the disk method, there's going to be times where we're going to need to take dy strips as well. These will be y values from C to D. All right, and then again, you can leave that pi on the inside, but even more so than the disk method, I'd encourage you to factor out that pi into the front of the integral so that it doesn't accidentally get squared in with one of these r measurements. Okay, it says, note that the integral involving the inner radius represents the volume of the whole and is subtracted from the integral involving the outer radius. Now, could you leave it like this and distribute the w to each of these and do two separate integrals? You could, but we're going to focus on being efficient and doing this in a single integral. Okay, so we've got our box here that's got our washer method in it. Make sure you highlight that in your notes. To find the volume of a solid revolution with the washer method, use one of the following formulas. All right, we've got the horizontal axis of revolution and a vertical axis of revolution. Similar to this method, that's going to be given to us. And so, okay, so for each of those, we've got our formulas. This one we've already seen previously. This is the one for a vertical axis of revolution when we're taking dy slices. All right, so it's important. The rectangular strip is always perpendicular to the axis of revolution, similar to perpendicular. We're going to say perpendicular. All right, for washer method, we still have to take slices that are perpendicular to our axis of revolution. So we're not going to be able to choose that like we did with our shaded area, our 2D area. We're going to be kind of go by whatever our axis of revolution is. All right, perpendicular steps. All right, we got some steps. I think we'll just go through these as we look at example number 2. So I might be sliding this up and down quite a bit. All right, so example number 2, and again, these are all meant to be calculator active for now. Just like with the disk method and with shaded area, you can have these types of problems on a calculator inactive section. It'll just be integrals that we've got rules for to be able to do by hand. Okay, but for the purposes of this lesson, we'll do all these integrals once we get them set up correctly in our calculator. So I want us to make sure we're focusing on setting these up accurately and that we're annotating our pictures so that we get accurate R big R and little r values. All right, so example 2, find the volume of the solid generated by rotating the region bounded by y equals x equals 0, and y equals x minus 1 quantity squared plus 1 about the x-axis. They give us a picture. Step 1 says draw a picture and shade the desired region. All right, so they've already done that for us. So let's go on to step 2, find capital R, the distance between the axis of revolution and the outside of the region. Okay, let's see if I can draw that. Let's go with blue. It looks kind of purple, whatever. All right, so in washer method, we're going to need to kind of do 2 measurements. You can draw rectangles or you can just draw kind of lines. That's going to be up to you. But first off, highlight your axis of revolution. We're going about the x-axis. This is our x-axis here. Okay, label that axis of revolution. That's y equals 0. And my big R. All right, we're going to have to take perpendicular strips, so they're going to be dx strips. So I want to go to the outside. This is our outside of our shape. That's determined by this parabola here. And so my big R value is going to be this measurement here from the outside to our axis of revolution. That's my big R. Okay, and I might write over here, because I don't have space over here with this crayon, that's going to be top minus bottom. And so top is my x minus 1 squared plus 1. And then my bottom is just y equals 0. You could put a minus 0 there, but I'm not going to. Okay, little r. Okay, little r is going to be the inside. It's going to determine which part is cut out of our solid if it was a disk, if that shaded region did come down to the axis of revolution and it was a solid disk. Okay, it's not. We're cutting out this part here, and so little r is going to be this measurement here. Okay, from the inside down to the axis of revolution. Okay, that's determined again by top minus bottom, so it's another top minus bottom measurement. In this case, this is our y equals x that we're given here. Label that y equals x there, and so top is going to be x, and bottom is 0. So you can say x minus 0 or just leave it as x. So whatever you put in is that same height value that you get out. Okay, so now to do our next step. All right, we did step 1 was given. We just did 2 and 3. Step 4 says find the area of the base of one washer by substituting your expression for big R and little r into the formula for area, pi times big R squared minus r squared. I kind of skip that and go straight to volume of a slice because it just adds on the width, and it's basically the same thing. But we can take this one step further and integrate it. And so this is going to be pi times big R squared minus little r squared, just times our width. That's the only difference in this area formula and this volume, is that third dimension of width, that thickness there. Okay, so if we take that and we do our first washer and we kind of apply it to this specific case here, pi is still out front. Now our big R, we need to substitute this whole business in, so make sure you use parentheses there, or you can simplify that. I'm going to be using my calculator, so I'm just going to leave it like it is, even though that would be an easy one to simplify. All right, and then we want to make sure that we remember to square it. And let's see, I think I need another set of parentheses here since I'm subtracting our little r, which is just x. I want to square that, make sure I close that, and then our w, since we're taking dx strips, is going to be dx. Okay, so then our next step is to say, hey, we don't want just the volume of one washer, we want the volume of our whole solid. And so we want to integrate that. Should have backed that up. That's all right. Okay, so we're going to keep the pi on the outside, and we're going to integrate. And now we need to look at our picture and know, well, where are we going to start and where are we going to end? Well, our shaded region, smallest x value is 0. So I'm going from 0 to whatever this intersection point is right here. So where does y equals x intersect x squared minus 1 squared plus 1? It intersects at 1, 1. All right, you can set those equal to each other and solve and find that value there. okay, either by hand or using your calculator, or I would be careful about just going by your graph of finding that intersection value. And then I'm just copying down the volume of my washer, the rest of it. Be careful about your parentheses. I'm gonna squeeze in my dx there. Okay, so that's what we would want to put into our calculator, okay? Or square it, simplify it, and integrate it by hand. That's one we could do by hand. But if we do that and we put it in our calculator, we should end up with 4.817. Make sure you go out to 3 units past the decimal. Okay, and again, if this was in an application problem with units, we would want to make sure that we give cubic units for that one. All right, let's look at example 3. Getting a crayon, take a sip of coffee. Okay, find the volume of the solid generated by rotating the region bounded by y equals 2. Okay, we've got that here. And this quadratic here about the x-axis. All right, so I got my highlighter. I'm going about the x-axis again. That's my axis of revolution. Y equals 0. Okay, so looking at this, again, step number 1, check. We've already got our shaded region given to us. It's bound by these two. It looks like we're going to be going dx strips again and going from 0 to 2. If you set 2 equal to this, then you're going to be able to solve for the 0 and the 2 by factor. Okay, so I need my big R. Okay, and that's going to be top minus bottom to that from the outside to the axis of revolution. Okay, so let's see. I'm going to do it this way. Volume of a slice. Let's start with our formula. We've got pi times big R squared minus little r squared times our width. We take that and we go straight to the volume of our washer. Then I can go ahead and plug in my capital R. All right, so again, that's outside. That's governed by y equals 2 minus the axis of revolution, which is just 0. 2 minus 0 is 2. That's going to be a constant 2 over the whole region. Square that because we're squaring our capital R. Okay, and now we need to find our little r. So our little r is governed by this parabola here. So on the outside of this solid, if you were just looking at it from like from just this part of the solid itself, you wouldn't be able to tell that this inside is cut out in this kind of convex cone shape here, parabolic shape here. All right, but it is, and we need to make sure that we include that in our little arcs. That's gonna, in the formula, it's gonna subtract the appropriate amount of volume that we need when we subtract our little r. All right, so little r. Let's make sure we put it in parentheses because our top is this parabola here minus the inside, which is our axis of revolution, which is just 0. So we're just going to square that parabola. Okay, so there's our little r squared. Close it up. Our width is dx. We're taking dx strips since we need to be perpendicular. And now we can integrate that. Okay, so the volume of our solid is pi times the integral, and at the beginning we said we're going from 0 to 2. Since we're going left to right, since we're taking dx strips. And we can simplify that to 4, one less thing to plug into our calculator. I don't feel comfortable squaring that out by hand. It'll be quicker and more efficient to do that. Let our calculator handle that. Okay, so there's our integral. That'll give us the exact value of the volume of our solid try to practice plugging these into your calculator, making sure you get the same thing that I get. We should get 13.404. All right, so let's see some of the similar tweaks that we did with the disk method. Let's see how they look when we apply them to our washer method. All right, so example 4. It says find the volume of the solid generated by rotating the region bounded by y equals 1 over x, y equals root x, and x equals 4 about the line y equals negative 1. All right, so we're getting a little more funky with our functions, and they've changed up our axis of symmetry so that it's not on the x-axis. We have y equals negative 1, so they don't show that line. So make sure that you draw that in and make sure that you make a note of that axis of revolution. Okay, they've already shaded in our region here. Okay, we've got our square root function here. I might go ahead and label that. And then this is our rational function, y equals 1 over x here. All right, going with red, orange to find our capital R, which is our step 2. I'm going to go ahead and set up our rule. Volume of a slice is pi times big R squared minus little r squared times W. And again, the way that we know to use the washer method and not the disk method is all of this empty space between our shaded region and the axis of revolution. Okay, if our axis of revolution was the line x equals 4, then we could use the disk method. Okay, we would just need to take dy slices. Okay, because that shaded region is touching the axis of revolution, but it's not. Our axis of revolution way down here, we have all this empty space. So we don't have a choice. We have to use the washer method between disk and washer method. Okay, so let's take that and let's find the volume of one of our washers for this example. And let's find our capital R. We said it was our square root of x, which is the outside function here. Oh, I gotta be careful. I marked that wrong. I went down to my x-axis as if we were rotating around our x-axis, but we're not. We got to go all the way down to our axis of revolution. Okay, I don't have an eraser, but whatever. All right, going all the way down to here. So that R value is going to be my square root of x minus the axis of revolution, so minus a negative 1. All right, you can write root x plus 1 if you'd like. That's probably what I'll type into my calculator. All right, that gives us our capital R. Root x minus negative 1. And let's find our little r. All right, little r is going to be the inside, which is governed by that 1 over x function, minus our axis of revolution, which is negative 1. So I'm saying minus, and then our little r is 1 over x minus that same axis of revolution, negative 1. All right, make sure you square it. Make sure that you capture that whole difference in parentheses before you tack on the dx. All right, I'm gonna go grab a calculator. We're gonna put this one in our calculator when we get to the integral part, because I want to show how we really need to be careful about our grouping in our calculator. Make sure we're communicating in the right syntax that our calculator understands. All right, so to find the volume of our solid, let's integrate. We're going to go left to right. We're going from 1 to 4. Again, those are those intersection points. We know 4 is our right edge, and if you plugged in a 1, root 1 is 1, 1 over 1 is 1. They intersect at 1 and 1. All right, and I might go ahead and also do these double negatives. All right, if any of this crayon mess is hard to read, as you're taking notes, feel free to open up the completed notes that's linked on Canvas, and it'll be clear on there. I guarantee you. Okay, got a calculator. Let's plug this in. Let's make sure, again, that we can do this with accuracy so that come time to do this on an assessment, that we can not blame any wrong answers on our calculator. All right, starting off with pi. Now we go math 9 for f and int. We're going from 1 to 4. And it's already got one set of parentheses for me, so I'm going to go ahead and do my capital R, square root x plus 1, close it, square it. And then for our little r, we've got 1 over x. All right, that became plus 1, close it, square it. All right, I'm gonna double check it before I press enter. I remember my pi, got the right A to B. Okay, looks good to me. Let's see what we get. I got 41.817, and that's what we're looking for. All right, if you got something different than that, there's no trig in this one, so we don't have to worry about radians versus degrees. So double check your parentheses, double check your exponents, and make sure you have a pi out front. All right, let's look at one more example together before you try some on your own. Okay, let's look at example number 5. Find the volume of the solid generated by rotating the region bounded by y equals root x. What colors do we have left? Ooh. All right, y equals root x, that's this guy here. And y equals x squared, that's this guy here. About the y-axis, ooh, the y-axis, that's different. So this is our first one with a vertical, ooh, I missed. With a vertical axis of revolution. All right, I'm going to go ahead and label that x equals 0. Okay, step 1, check. Step 2, find r. So now here's where we need to be careful, because our r value is no longer going to go top minus bottom. It's going to go outside minus inside still. We've been using that same language, but now we got to kind of reorient as if our picture is like this. Okay, so turn it if you need to in your mind or your actual paper itself. But we want to go to the outside curve, which is going to be this guy here. So our big R is going to be this to our axis of revolution. And because we're going to need dy strips, we're going to need to rewrite our functions x in terms of y. Okay, so before we do that, I'm going to go ahead and write down my formula for volume of a slice so I don't goof that up later. And now I'm going to come in and say, all right, so my y equals root x. If we square both sides, then I'm going to get x equals y squared. All right, so that's going to give me this top curve here, but for this one in particular, I need my other function. Okay, so if we take our y equals x squared and we square root both sides, then we get x equals root y, and we want to make sure we consider the positive and the negative. But since we're in this first quadrant here, since we're in this first quadrant here, we just need to consider the positive root. All right, the negative root does not come into play in this shaded region. Okay, so we can keep it positive. Okay, so there's that one. So this r value here, this capital R, And I may write that down separately. Is going to be outside, which we said was root y, minus the inside, which is 0. So that's just going to be a root y. Our little r, which is going to be this inside piece here from our axis of revolution to the inside of our curve here, which was our green curve. If we solve x in terms of y, is y squared minus our axis of revolution, which is 0. Okay, so coming back to our volume formulas, let's go to our washer. Let's apply it to this function in particular. We've got pi big R squared, so that's root y squared. Coffee's making noise. Minus little r squared. I'm gonna put that in parentheses so it doesn't look so weird. And then times our w, which is gonna be dy. All right, let's extend that to our whole solid. That means we need to integrate. Okay, this time we're not integrating left to right, we're integrating from bottom to top since we're taking these dy slices, since we gotta be perpendicular to that axis of revolution. All right, so we're going from 0 up to 1. And root y squared is just y. Pi's on the outside. And y squared squared is y to the 4th. Be careful about trying to simplify that. Leave it like it is. Let your calculator do some work. Okay, if you put that in your calculator, again, you can swap out the y's for x's. You'll get the same value. We should get a little bit less than 1 cubic unit, 0.942. Okay, so those are things you want to look out for, is changing the axis of revolution. Make sure that you're making note of what that is for each problem. I'd encourage you to highlight it, point it out in some way on your picture. Make sure you're finding capital R and little r separate from each other, and then plugging them in to your volume formula. I want you to try examples 6, 7, and 8 on your own before you go on to part 2 of the part 2 video for this section. All right, try 6, 7, and 8. 8 asks you to do multiple volumes on the same figure. Just make sure you pay attention to what changes in each part. And then watch part 2, check your work, and good luck, do your best. You got this.